right, hi everybody. Welcome to the first day, Failure of Materials in Mechanical Design. My name is Allison Dunn and I'm the instructor for the course this semester. And this is an EDGE course. So please visit the Canvas e-learning course website to peruse the syllabus and see any communications that are there. That's really going to be the best way to communicate outside of class through there. You're welcome to send me messages through there, use the class discussion board. That's really the best way to interact. The class is going to be very much like you see here, and I am going to be using the tablet that I have here to teach the class. But the slides that I'm going to put up are just blank. So we're all taking notes together. If you, so there's really nothing to sort of download ahead of time or something like that you'd be filling in the blanks. I may provide some pre-lecture materials just for reading later in the semester so that you can come in a little bit more prepared for class. But it's basically just going to be the pace of my writing on the tablet is the pace of the class. And so I'll talk a little bit today about framing the course and what we're going to be doing. But I want to save most of the logistical questions to the end because there are distance students, there are in-class students, and so I really want to preserve the recorded lecture time for the technical content, and then we'll deal with logistics more toward the end. So that if somebody is watching this later on, they don't want to hear that, they can stop the lecture at that point. Does anybody have any questions now before we get started that you think can't wait until the end of class? No? Okay. So here's how I'm going to do it. There's just a blank slide. All right, so first I'll talk a little bit about framing the course. All right, so is that seeable or is that still a little bit small? Meh, we got some hands like this. Okay. For me. Okay, good. I'll try to write a little bit bigger. And then I plan to provide my written notes after the class on Canvas. So you can take notes, you should take notes, but my handwritten notes will be uploaded sometime after the class. So the name of the class is about materials and mechanical design. And so all mechanical components are made of materials. I'm going to write everything down, even if I write slower than I talk, so that we're all on the same page. So it may seem a little bit slow at first, but I do have some plots and things that I'll be drawing later on. So components are made of materials. So when the material fails, right, then the component also fails, right? So that's the relationship that we're talking about here. And when we say failure, there are many, many different definitions of that. So what does failure mean in this case? It means that the component is performing outside of its intended function. All right, we're having some pen issues here. Okay, so performance, outside intended function. All right, and so what we need in order to prevent this from happening is a variety of techniques. And so we're going to do analytical techniques. All right, so we'll start, some of the things in the class that we do are going to be starting from first principles. We're going to go back to stress and strain, and the calculations that we do will have kind of an exact answer based on what we would predict. And then there's also some empirical techniques that we're going to look at. So empirical means not from first principles, but developed based on measurements in a lab or hundreds of years of experience, and sort of these laws that have bubbled to the surface and are widely accepted. Okay. And so performance outside an intended function can take many different forms. And so there are 4 ways that the failure in components tends to manifest. All right, so the first one is elastic deformation. And you might think, well, if things are in elastic deformation, then they're working as intended. They're not breaking. But if something is bending more than you would expect, like let's say your chair leg, and it bends so much that it goes too far, then the chair could fall down, right? Even though the material itself did not break or have plastic deformation, right? Elastic deformation means there's something out of place, and that could be considered a failure. The one that we're most familiar with is plastic deformation. Right, and we're talking about mostly ductile metals in this class. So plastic deformation means something that has changed dimension or location permanently. It's not going back. So plastic deformation. We can also have ruptures or fractures. Right, so rupture can be a fracture that has propagated all the way through. You can also have a rupture, could be like a plastic collapse, where you have a big truss structure and it starts to yield, and then it yields further and further such that the whole structure collapses. And then we can also have failure due to material change. Right, so we're all familiar with things rusting, right? So that's a material change. It can be chemical in nature, like that. It can be metallurgical changes, right? It could change the grain size of a surface of a metal component, or there can be other changes that happen that are not very common, like nuclear materials and things like that. So these are the 4 kind of major manifestations of material failure. And these can come from a lot of different mechanisms or agents that act on the component and, because of that, act on the material. All right, so next is failure. Try to write bigger. Failure inducing agents. And so there are 4 that the book identifies. So that's what we're going to focus on, and then I'll point out exactly which ones we're going to talk about in class. So the first one that we're very familiar with is force, right? When we apply forces to things, then they will often move. And so there can be many different types of forces, and we're going to look at all of these in this class. So the first one is steady forces. Right, so forces that do not change in magnitude, that's a steady force. Right, transient forces. Forces that continually change in magnitude. And potentially direction. Cyclic forces. These are very common in mechanical components, like a wheel rotating induces cyclic stresses or any kind of repeated motion. And then there can also be random loads applied, or random forces. Okay, and so we're going to look at all of these in this class. And you might think, well, random forces, how do we do that? Well, we start to bin them, and we look at their intensity and their time signature and things like that. And so we'll look at the way that all of these types of forces affect materials. We'll look a little bit at time as well. So there are a few time scales that you've probably studied. The first one is very short time scales. And when I say very short, I'm going to characterize that as like dynamic or impulse time scales, like very, very short. We're not really going to study too much about really dynamic systems. This is more of a basic course in that. There are also short time scales, right? And we may study some of that because oftentimes forces are cycling over short time scales. And so we will need to take that into consideration. And then the one that's really quite important is the long time scales, right? So there are effects that happen over long times like creep, right? So if we have a steady force over a very long time period, that's when creep tends to happen, especially if there's an elevated temperature, right? And so you'll often have multiple of these things happening at the same time, but you can characterize the system by these failure-inducing agents to try to give you a map as to like, where do I begin, right? So what's the most important thing that I need to take into consideration? The next one, I gave a hint, is temperature, right? And so there are many different types of temperatures, right? We could talk about very low temperatures. That's really not going to be too much of a focus of this class. We will talk about a little bit how temperatures affect material properties, but we're not really going to talk much about operation at low temperatures. We will obviously talk about like room temperature, standard temperature and pressure. That's where we start every time. We can have elevated temperatures, which are often seen in mechanical components due to rubbing, due to continued deformation, exposure to the sun, exposure to other things, right? And then we can also have steady temperature, which is what we like. That's the easiest to model. But we can have temperatures that go along with these other kinds of forces up here. So I'm just going to make like a bracket up here, and I'm going to make like an arrow. So we can also have temperatures that are transient. That becomes a combined heat transfer and mechanics problem. We can have temperatures that are cyclic, right? We often see that with the circadian cycles, or we can also have temperatures that are random. That's not as common of a case. And then the last agent that can cause failure is reactive environments. All right. So that can be oxidation type chemicals, that can be nuclear environments. So something that is causing the material to change its character, like fundamentally at a chemical level, which would then change its properties. Right. So the last thing I want to say about this is there are two locations of failures that these agents can work on. And there are only two. So the first one is inside the body of a component, right? So if we're working with a component and inside the material somewhere, we determine that's the highest point of stress, and we apply some failure criterion or something, we could say, okay, that is a body type failure. Then the other location is at the surface of a component or a material, and this is actually the much more common one. And so if you think back to courses you've taken where you looked at a beam, right? A cylindrical bar, maybe it's an axle, maybe it's rotating, and if it has different dimensions on it, then where it changes dimension, those are the stress concentration points. So any bending moments or other loads on that shaft are going to cause failures first if the loads continue to increase at those locations which are on the surface. The surface is also exposed to reactive environments, and depending on surface finish, can be the location of initiation of cracks, defects, and things like that that act as stress concentrators at the micro scale. Okay, so the focus of today's lecture is where we start with most mechanical design considerations, which is what is elasticity, right? So we really want most of the things we are working with to stay in the elastic regime, but we have to understand what is elasticity in order to make sure that that happens, because it really determines what sort of techniques we use to analyze things, right? and we're talking about ductile metals here. So let's say we had like a cylindrical bar, right? So just a long vertical cylindrical bar. This is very common in all of our classes. And if this is made of something like aluminum, let's take a little section and like sort of zoom in to the molecular level. Let's see if I can sketch this a little bit better here. Right? And if we go down to the molecular level, we will get a unit cell of the crystalline structure of that aluminum. So if that's our unit cell, we would have atoms at the corners. I'm going to draw those. And then aluminum is a face-centered cubic. So on each of the faces of this cube, we would also have an atom in the center. I'm not going to draw the backside. I'll just draw the visible planes. Right? And so when we think about this crystal structure and the sort of relationship between each of these atoms with its neighboring atoms, right? We can think of all of these, if you want to, as like a giant truss, right? So they're all together at the microscale. There's millions and millions of them. And so if we push on the whole bar or pull on the whole bar, each of these little units is going to stretch or contract correspondingly. And that's where elasticity comes from. And it's described in terms of the energy as two atoms are coming closer together or farther apart, right? You can't push two atoms together, at least in an aluminum like this, until they're touching, right? Because they never really touch, they would repel each other due to their electron clouds and nuclei. And you also have a hard time, we know this, of pulling atoms apart, right? Because they have an attractive force. And so the bond structures here hold the atoms in equilibrium where they are in this crystal structure based on how it is bonded together, right? And what the atomic structure is, not just the molecular structure, but like down to the atomic scale. So the way that we understand this, and I'll show you how this relates to our definitions of stress and strain, is we can think of how the energy changes of bringing two atoms close together. So I'm just going to draw like a little schematic up here. So we have two atoms. They're in some sort of a crystalline lattice. I just drew bad arrows between them. And so we can draw in a plot where we have force on the y-axis. And this is going to be the interatomic force, the force between only those two atoms. And so then what we want to do is on the x-axis, we'll have the separation distance. Right? And we'll call that lowercase r. And so let's talk first about repulsion, right? We can't smash those atoms all the way together. And so as they get closer and closer, the force is going to increase up to like infinity. So I'm just going to draw sort of a schematic like that. Okay, so we go along. If they're far apart, we don't have any repulsion because they're not far enough apart to affect each other in that sense. But when they're very close together, we get a force like that. Okay, let me write repulsion here. Okay. And if we then try to talk about attraction instead of repulsion, we get a similar curve, except the force goes in the opposite direction, right? So an attractive force wants to pull things together. So we're going to call that negative, so in the opposite sense. And it's kind of going to go like this, right? So attraction there. And when we add both of those curves together, whoops, the way that they add gives us a resultant curve. Just draw it in red. So it's going to come down. I will try to do my best here on drawing. Okay, and then it's going to go back up and asymptotically go down to zero force at infinite separation, where attraction and repulsion no longer occur. Okay, and so where that red curve crosses the x-axis, we're going to call that an R naught. So that is where the atoms sit when they are happy, when they are not being stretched in any kind of direction, where this crystalline unit cell is at its happy place, right? The repulsion and attraction are balanced out, okay? And so now you can think about what happens when we stretch this. I think I'm just going to keep going on this slide for now. Question?
Just to be short, at close distances, the repulsion is greater than the attraction, like super, super close distances.
Yes. So these curves, the way that they're shown in most textbooks is that they just go up and then trail off. But if we continued to draw them, yes, the repulsion would have much higher magnitude than attraction. Yeah. Okay, so if we stay on this plot and we think about kind of what we can approximate from it, I'm going to change colors to green. And so if we come through and we draw like a slope right here, right where it goes through 0, we can draw a tangent to that line. And that tangent, we can say, is kind of a linear approximation. So if we push two atoms together, then there's a proportionality constant between how far we pushed and the force we have to push with, right? And so this is called the Condon-Morse force curve. So I'm going to draw that here. Condon. This is just the name of the people that worked on it. I'm going to try to bring that in through the class so that you know a little bit about the scientific genealogy of the concepts that we're learning about. And so if we draw that linear approximation, then we can say that if we sort of apply that then now through the whole component, then all of these tiny fractional changes will add up to the overall change in length, okay? And so you can say that the overall length in change, like the change of length of a component, is the sum of all of the individual stretching or length changes from all these individual cells. So that's the theory. And we would say then, if at the atomic scale, I'm going to write an equation here. I'm going to say eta, which is that Greek n, is equal to whatever our separation is minus the equilibrium separation divided by the equilibrium separation, right? We were very familiar with these kinds of equations. We might say initially, oh, it's a percent error, right? Exactly. It is a percent error. It's also like the atomic engineering strain, right? Or it's called the fractional interatomic spacing. And you will also recognize that that equation is identical to, I'm going to switch back to a different color here. It's identical to our definition of engineering strain, which is epsilon is equal to whatever our deformed length of some dimension minus the initial length, that's supposed to say L naught, divided by L naught, right? So that's our definition of engineering strain. And so from this kind of understanding where we can draw that tangent line, that there is a coefficient that describes the relationship between those two, we can say that the force, right, is proportional to strain, right? Or the force is proportional to elongation for any component or at the atomic level of this crystalline lattice. And that's only in 1D, right? So that's just atoms or maybe a component in 1D. But if we extend this a little bit and we say, okay, I don't have a component that is one atom around and then it's long. What I really have is a bar. So if I normalize by area, right, then I can say F over A, which I'll just say is equal to sigma. Let's call it an axial stress. That is now going to be proportional to strain. Right? So this comes directly from this atomic model. And then if we continue following this, we might recall Hooke's law, where we don't just know that stress is proportional to strain, but we know that stress is equal to, in one dimension anyway, the Young's modulus times the strain. Right? So then we get out Hooke's law. Okay. And so some of these laws like this that come out are really great because you can derive them in a bunch of different ways. You can derive them from atomic models, you can derive them from experiments, you can derive them from stress states. So it's all very cool. This is very helpful, right, in understanding like what is elasticity? What happens when I push down on a material?
Yeah.
Question.
The Young modulus, is that the slope of that green line?
The Young's modulus is not the slope of the green line on a force separation curve because it's not the same units, right?
Is there any relation between that slope and the elastic Young modulus?
So if I just look at this line and I say, what is the slope of it? It's the force divided by distance. It's essentially a spring constant, right? And so there could be a relationship between this curve and the elastic modulus if we somehow accommodate for that other dimension, right? But I don't think so. I'm thinking back to like some molecular dynamics modeling that I've seen if I know that there's a specific relationship, because in molecular dynamics simulations, they use these kind of energy potentials between all of the atoms, and I'm trying to remember how that scales up. There was a comment in the back?
Yeah, what if we normalize the r-axis with r0? Wouldn't that be closer to the Young's modulus, or what would the physical meaning of that be?
So the question is, if we normalize, I'm trying to repeat the question now. If we normalize the x-axis r by r naught, so we have a normalized axis there, then could we possibly find a relationship between the slope of this line and the Young's modulus? I'm going to go with no. I'm just going to say that beyond thinking about the atomic scale, there's only so many ways we can make this analogy work perfectly between them. And I don't think that you can just scale this up. There are trends that you can find. And I'll talk about that, I think, on one of the latter slides. But there's so this, we're talking here, I use the example of a face-centered cubic, right? I think, did I say body-centered or face-centered? Okay, face-centered, good. I just wanted to make sure I said the right one. So I use the example of a face-centered cubic, but there are many different crystal structures, right? And so depending on which one of those you have, it'll change these energy or force separation curves, and then it will also vary between materials. There could be two metals or two alloys that have the same crystal structure, but they don't have the same elastic modulus. And so I think I'm going to go with that answer.
Did you say that eta had a name here? Does the constant have a name?
Engineering strain.
Eta is
Oh,
also-
eta, sorry. Eta is the fractional change of the interatomic spacing.
There's no show, okay. I was wondering
There's
if it was
no-
like Condon-Norris constant or something.
No, I don't think so. Excellent questions. All right. So this is really helpful, but unfortunately, we know from other undergraduate classes, from pulling on materials, that they don't fail. Typically, ductile metals don't fail in a tensile fashion. If I take a piece of aluminum or steel or something like that, and I put it in grips, and I pull on it until it fails, and I open it up and look at that failure surface, I'm not going to see a straight line across, right? So we can't get everything we need from thinking about these 1D problems. So we have to think a little bit about shear as well. Okay, so shear is how we're going to consider moving sort of to the extent of elasticity and maybe into plasticity. Okay? So let's look at the side of a crystalline lattice. I'm just going to draw it big. So I'm just going to draw two boxes like this. And they're going to have atoms at the corners. Okay? And we can number them, and we can label some of these dimensions, right, like our equilibrium atomic spacing. And now instead of pulling on one of these along some dimension, we're going to shear across the top and bottom. So I'll draw a shear stress to the right on the top and a shear stress to the left on the bottom, and I'm going to label that tau. Right? Tau is the variable we often use for shear stress. And so if this shear stress is applied, then we are going to just say that the atoms, let's say on the top, are just going to move over to the right. So I'll just draw little arrows here, so they're just moving to the right. And here's their new location. This is a uniform shear stress along that plane. So it just deforms the whole lattice structure like that across the top and just moves everything slightly to the side. Okay? And so that's if we apply sort of a little bit of shear stress, something where we would not expect it to go out of some kind of linear regime, right? It's still sort of on that approximation of the linearity in the separation curve. But if we keep going, right, we keep shearing this thing long enough, these are really not tethered. The lines that I've drawn, they're imaginary, right? Really, there are electron clouds, and these atoms sort of are fixed in, well, relatively fixed in space with relationship to each other. So if I keep shearing it, I'm going to stretch the distance just a little bit between the atoms on that top layer and on the bottom layer. And if I keep going and I keep stretching, I'm going to eventually get those atoms on the top not close to where they were, but actually closer to where the next atom started, right? So if I push, I keep going, right? Let's pretend there's also like another one over here, right? Then they would move all the way over to the location where the other atoms were at the beginning, where their neighbor was, right? And so this is the way that atoms slip against each other in a crystalline lattice, okay? And so this is considered when the lattice has slipped. And so you can see now that this is like a cascading event, right? So it can happen all at the same time, but let's say you have one location that's experiencing more shear than another. Well, that one's going to slip, and it's going to cause the next one to slip, and the next one to slip, and it's a cascading type event, right? So early theoreticians, they postulated that this happened all at the same time. They said, listen, I can take like a very crystalline material and I can push it really hard, and it looks to me like this happens all at the same time, right? This thing goes and everything slips. And so they tried to theoretically calculate a stress under which that would take place, right? And so they said, okay, if I go down to this atomic scale and I sort of, try to calculate what is this threshold shear stress, and then I multiply it times all these atoms in a real situation, they got something exceedingly high. So they found a threshold stress that was on the order of like millions of psi. So let me, M, right? And so they said, okay, well, that's a bit high, because really, when they measured it in the lab, theory and experiment, it was much lower, like hundreds or thousands of times lower. So it was actually 10 to 50 KSI, right? So it's about 100 times lower. And so they had to go back and think about this again, right? Because they said, okay, if all of a sudden I'm pushing on a material and then it yields and I can see it sort of at the micro scale, to me it looks like it happens instantaneously, but clearly it can't be, right? Because we would need to have a much higher shear stress to have all those happen simultaneously, which we don't have to have. And so there must be something more progressive that is slowly moving through the material, slowly, but faster than we can see. And so that's when dislocation theory began, and that was in the 1930s. Right. Where they thought a little bit more about defects in the material and locations of highest stress, and they thought, okay, we initiate something, and then that slips across and causes a cascade, and then when I look at it in the lab, I see these massive layers have moved. Massive, I mean like microns, right? Okay, so I'll just draw a couple of pictures of dislocations for you so we can get back into that, understanding a little bit. So dislocation basics. All right. So let's say we have a grain of some ductile metal, right? So I'm going to draw some grain boundaries away from it like this, right? So this is some kind of a grain. Usually they have a few more facets than this, but this was easier to draw. And so what happens when you like sort of zoom in, if you use some kind of microscopy, is that you see slip bands in the grain. So I'm going to draw them in a different color. And you see them clustered together. But if the grain has the same crystal orientation, which is kind of the definition of a grain, then all of the bands you see will go the same angle, right? And you'll see the bands that tend to go all the way through one grain, but they usually don't go over onto the next grain at the same angle. And that's for two reasons. The first reason is the next grain might have a different angle of its crystalline structure. So it's hard to kind of change direction with dislocations, right? We'll talk a little bit more about that in the next class. But they like to go in one direction, okay? So it's hard to change directions. And the second reason why they don't really go through grain boundaries as easily is that there's the grain boundaries are where there's more opportunity for impurities, other defects, toughening agents, et cetera. And so cracks don't necessarily propagate along grain boundaries. Sorry, not cracks, dislocation bands. We're not at a crack just yet. So when this happens, and when this was first studied in the lab, they polished a surface to be very, very flat, right? As atomically flat as they could get it. And let's say it's something like single crystal aluminum or something like that, right? And so they know that in this aluminum, the crystal structure is all oriented, right? It's a single crystal, so everything should be oriented the same direction. And so then if they take and they have a sort of an atomically flat surface, and then they apply some shear stress to it in some direction, then some of the material will actually start to pop up in like little bands, right? And this is at like this is also at the molecular scale. So the material will sort of pop up above the surface like that, and you'll get these little projected bits. And what really is happening is that is a slip band that goes way deep into the material, but you just see it at the surface because you started with a very flat surface. So those things tend to stick out now. So that's one way that early scientists visualize these things. And so the slip bands themselves, just to give you an idea of how far these things go, the distance of like between two slip bands like that would be about 1,000 atomic diameters. So they can be very big as far in terms of like the atomic diameters. That's why they could see them coming out, because they couldn't see an atomic diameter, which would be like an angstrom, right? Very hard to see in microscopes of the 1930s. But if you got up to 1,000 atomic diameters, right, that's 100 nanometers, 0.1 microns. That's kind of the resolution that people could look at. And then so that would be like how far they slip. And the thickness of the bands is something like 100 atomic diameters. And so this is kind of just characteristically how these things look. This is how they come out. All right. Based on crystal structure and how things typically happen. So this is just sort of, I just wanted to give you an idea of the dimensions of this, of how those dislocations are moving. Okay. So when we talk about these slip bands and dislocation motion and how it's oriented in a crystal structure, we have to start talking about angles a little bit. Okay. So I'm going to go to the next slide here. So let's go back to our column of material, right? A cylinder like this. Okay. And we're going to apply a force, a tensile force at the ends. This is how we always start in our mechanical engineering schematics. We have a bar, we apply a tensile force at the end. Okay, we know that, that shear is what leads to these dislocations moving, and we've studied a little bit about what happens, and so we know that these things fail at an angle. And so if they fail at an angle, we can say that that is the slip plane, right? So I'm going to try to draw something on here that is going to be the slip plane. I'm going to do my best here. It's just going to be, ooh, not bad. Okay. And draw some hatch marks on there. So this is our slip plane, right? And so if this is a ductile metal of some ideal thing, it's at a 45-degree angle. And if we were to draw a normal to that plane, oops, here's my normal arrow, right? Then that would exist at some angle away from the force that I have applied, and we're going to call that psi. Okay, that's what the book calls it, so we're just going to go with that. And so psi is the angle between the applied force and the normal to the slip plane. Okay. Now, so that's our slip plane, and the way that we determine that is it doesn't have to be right there. It could actually be at any angle around, right? So it depends on if there's any defects in this or any on the surface or whatever, what angle that is, right? So it can be any rotational angle within there, but it is going to have its surface normal at some angle with respect to the force. So that's the plane, and now we can identify from that plane a slip direction. The slip direction is in the plane somewhere, okay? We don't know what direction in the plane, but we know it's in the plane. So we could take and draw a second vector. Try to do it in a different color. And it's going to be somewhere in that plane. So I'm just going to draw it kind of like randomly out to the left, if my pen will work. There we go. So it's in the plane. And that is going to be defined away from the force by some angle. We'll call it lambda. Okay. So now we have, and the normal to the slip plane and the slip direction are perpendicular to each other, but they can be at any angle sort of rotated around in there, right? And so we can start to define some geometry in here. So we can say that the area, let me go back to red real quick, hang on. We can say that this area is the area of the slip plane. I'm going to call it ASP, and that's equal to our sort of projected area on the top. We'll just call it A, right? It's going to be pi r squared, or whatever, divided by cosine of psi. Okay? And so it's going to be larger than the projected area at the top. It's going to be rotated. Question? Psi plus lambda. I do. They're perpendicular to each other, but are they
They're both based off of the vertical, so.
If it's
Did
at any angle on the slip plane, it could be some random angle.
Yeah, lambda is a random angle between 45 and 135, if psi is a 45 degree angle.
So lambda can go anywhere around that. So we could actually here, let me just draw some other angles to help answer the question. So we'll go purple. So we could have lambda here, we could have lambda here, like anywhere. If that slip plane area ASP is like a pizza or a clock, right? That it can slip in any direction in that plane, right? So I don't believe that those would add up to 90 because lambda can be acute, lambda can be obtuse, and so we're already above 90. So I don't know that there is a like some expression between them or something like that. And so so that was my 5-minute bell. And so what I'm going to end on today is that there's a threshold shear stress that I'm going to say is little r because it's resolved into this shear plane. So in the shear plane, according to the slip direction, right, which is defined by lambda, let's just say it's defined by my original green arrow there, right? That means there's some shear stress also applied in that direction. So that's our tau r. That's what we are going to have an expression for here. And so tau r is going to be the force in the slip direction divided by the area of the slip plane, right? So we can just combine the expression that we had before, which was for the area of the slip plane, it was A divided by cosine psi, so I just flipped that over. And then the force in the direction, in the slip direction, sorry, I forgot to write down that expression. So the force in the slip direction is just F cosine lambda. And I don't believe the magnitude or the sign is taken into consideration here. So it's just a magnitude. And so if we plug that in as well, then we get our applied force at the beginning times cosine psi times cosine lambda divided by A. So I'm just going to circle that or draw a box around that. So if these orientations can be measured, and if we know the force that's applied to the bar at the beginning, then we could estimate what this, the resolved shear stress is on that slip plane to try to say, is there something for like that describes all BCC metals or all FCC metals or something like that based on how they act, right? And so this is called a critical resolved shear stress. And it is also known as Schmidt's law. So I'm going to write that here. Okay. All right. So we can play around with geometry like this and learn a little bit more about the origins of how we start to think about elasticity on the atomic scale. On Thursday, we have a 2-hour block in the class. So we're going to continue a little bit more with dislocation theory and how dislocations move around. And then we may also start to show that you can derive some of these things from experiments, and we'll talk maybe about stress states too. But this is kind of the background of the course before we start saying we have this thing under, cyclic loading and a high temperature and all of these combined things. Before we get to that, we have to know what is elasticity, how do we define stresses, where they come from, and things like that. So I'm going to close with the technical part of today's lecture, and then I'm just going to open it up for questions about how the class runs and what you can expect or something like that. Question here. So you do need the textbook. I think I put a note on Canvas about this. I put a copy on reserve at the library. So you're welcome to go use it at the library. You go to the reserve desk and tell them, I want to use the book for EML5233. They'll give you the book for 2 hours or whatever. So if you want to use it in short stints like that, you can, or you can buy the book. I will be assigning some problems from the ends of chapters in the book. And there's not a lot of reference tables in the book, so you don't need that. But the material is also laid out there, and I'm omitting a few of the things. The textbook is more comprehensive. So if you want to go back and read through the logic and get all of the details, then you should have the book. Yeah. Okay?
Oh, more questions?
Yes.
Concerning exams, are they like 20 questions, multiple choice, or are they free response answering like 3 questions?
I have planned for the exams to be take-home exams to accommodate both people on campus and people doing the class distance. So I release the exam, you have a week to do it and turn it back in. And it's going to involve some problem solving, like with equations and short answer. So because it's not a timed exam, it's going to be a little bit longer.
Right.
Mm-hmm. Yeah. Okay, I think we have to close. I don't want to go over, but I'll see everyone on Thursday. So thank you.
So thank you.